This is an overhead of the of a what type of reaction? I've got sucrose here, and I'm going to break it apart into its glucose and fructose. So that would be catabolic, and it's exergonic. That is, I'm going to be losing energy. This is also, by the way, called hydrolysis. That is the breakdown of a molecule as opposed to dehydration synthesis. So anyway, this is the enzyme. This is the enzyme substrate complex. This is just another depiction of what we were just talking about, maybe a little better drawn than what I was talking about. All right, and so kind of, we'll come back to enzymes a little bit more later. I just wanted to go over a couple of things about that we sort of alluded to. One thing is I can represent the different types of reactions by using this type of drawing or this type of graph. And this is showing you the amount of energy that was as part of the reactants and as part of the product. So in this case, the reactants are running downhill. That is, I had more energy in the reactants than I did in the products. So what kind of reaction would this be? This would be an exergonic reaction. That is, I'm losing energy. It's also going to be a catabolic process. And the delta G in the system is going to be negative. In other words, I am losing energy from the system as things break down and become more disordered and less energy available to do work for another system. Okay, so this is a way of describing that. This is the actual delta G. You can also do that for an endergonic reaction, where my reactants have less energy than the products that they will have at the end as they become more ordered, and I had to put energy in to make those products. So this is an endergonic or anabolic reaction. By the way, anabolic and catabolic are referring to putting things together or breaking them apart. Endergonic and exergonic are referring to the energy per se. And this is, in the case of energy, a positive delta G. So again, this is just using the delta G concept that we talked about earlier. Now, another concept that we were talking about was energy coupling. So let's just look at this for a second. So if I was having that reaction, A plus B is going to give me AB. Let's say, for example, that I put 2 ATP in here, and then I'm going to end up with 2 of the byproducts, okay? And remember that we said that some heat could come off of here. In this case, it's going to be coupled with the reaction C plus D and making CD that is going to use the energy that is coming off of there to drive this reaction as well as this reaction. So these two reactions are coupled, meaning that the leftover energy from this one is driving this one. So let's say, for example, that I put 14 kilocalories of energy in. That is 2 ATP, right? And I'm going to only cost 10. All right. So how much then is left over to drive this reaction that costs 2? All right. So I'm going to have how much heat left over? And if you got the answer of 2, you're good to go, right? That is, I had 10 going into this one. I had 4 left over. This one costs 2, and that leaves 2 coming off as heat. So the coupled reaction still makes heat. All right, so that's an important thing to know. Another thing, and I'm just showing you these because a lot of times they use these as ways of describing how enzymes work. And so what they're talking about here is that enzymes are providing what they call energy of activation. Now, a lot of times they'll use the boulder on the top of a hill as an example of this. That is, these reactants, if I rolled the boulder over to the edge of the hill, it would spontaneously go to this product, or that is, it would roll downhill. And the energy of activation is the rolling the boulder to the edge of the hill. So this is called EA. Now, energy of activation with an enzyme is going to be less because the enzyme is basically grabbing the reactants and moving them where they need to be. All right, so In other words, maybe the actual energy needed here is not a lot, or the energy is provided by the enzyme. And so this is lowering the energy of activation. So they sometimes will have a diagram, it's very confusing to look at, where they'll have, this is the transition state, they'll have the energy of activation without an enzyme, then they'll have the energy of activation with an enzyme, and then of course delta G is just reactants to products. The total amount of energy that was, you know, in a system was the whole thing, right? So there's different ways of looking at this diagram. So check it out in your book and just kind of understand what each of the parts